Hello everyone, my name is Wei-Ting. I'm from NOAA Air Resources Laboratory and George Mason University. Here I'm going to talk about a machine learning-based wildfire spread model developed in LL. As we all know, wildfire is critical to air quality in terms of fire emissions, and fire spread actually is a very complicated process. It requires lots of computational resources and detailed parameterization to simulate, which this may not be very applicable for near real-time air quality forecast. So we want to use a machine learning model which is more computational efficient. So the idea of this model is to predict the propagation of fires. We will select fire frames with fire as a center, as you can show here on the upper right. So at time t, we will have fire at the center, and the fire will, for example, move northward at time t plus 1. What we are predicting is this northward movement using the input variable list here. And we are using hourly fire radiation power, the FRP, so we actually are predicting the fire at the next hour. So here shows some preliminary results. We evaluate our model with 5 statistical parameters. The Hamming distance describes the difference between two frames. So that means that the lower HD, the lower Hamming distance, means the frames are more identical. Overall, the model underestimate the FRP values with negative biases. Like you can see, the bias are about -20 or -50 for strong fires, and the mean relative errors is about 0.7, which means our model underestimates the FRP value by about 30%. But if you look at frame similarities, model does quite a good job in capturing the spatial distribution with Hamming distance less than 2. So as we can see from the figure on the right, there's two examples. One is for strong fire case, one is for weak fire case. We can see although our model underestimates the FRP values, but it really captures the spatial distributions of fires. They also try to put the fire frames back to a coordinates map, as we show here. So the figure on the left is the current hour time t, and the figures on the right are the fire distribution are at time t plus 1. So overall, models show quite good agreements in fire spatial distributions. However, it cannot see the distinguished fires as shown in the green circles here. You can see that there's a forest fire at time t, but actually it's just gone in time plus 1, but our model still sees it and think it's still propagating. Another thing is our model focuses on current fires, and it don't have information from the new fires, so it cannot create these new fires. So in this case, the central US is quite quiet at time t, but there are lots of fires pop up in the next hour, and the model cannot capture those new fires. So here's just a summary of our work. We actually have an oral presentation about this model with more detail and more results to show in the upcoming MS Forest and Fire Conference in Minneapolis. So that's it. Hope you like it. Thank you very much.